intro, and thanks for providing us this opportunity to introduce the Energy Informatics Lab. So I'm going to talk about this new domain for us. So Energy Informatics. That is, from our point of view, uh, to exploit artificial intelligence, machine learning, optimization tools, algorithm, visualization, high performance computing. So all these within the domain of energy. So to handle challenge that exists in the domain of energy. So you probably already noticed that, I mean, the combination of energy domain and using informatic techniques and tools is very interesting. So that is why basically why we establish the a new lab at the Department of Informatics, which is Energy Informatics Lab. So here we are, the core team of the Energy Informatics Lab. We have a very diverse expertise, and that enables us to handle wide variety of projects and, let's say, more comprehensive projects, because we can tackle all in one basically. So today I'm going to focus on our our expertise and the domains that we believe that we can contribute and that are very relevant to the domain of energy. And here are the list, but of course not limited to this. I'm going to start with the data analysis basically. So here you see the pie chart of the process of data analysis, which start with data decision, data collection, then cleaning the data, doing the analysis and interpretation, and doing the visualization part. What happens basically in the industry, so some industry, I would say, not all. So they are interested in the nice piece of the pie, so that they go for the visualization directly, not going for the whole process. So they are interested in the part that they can actually see the data, see what they are expected to see. But sometimes they don't know what is behind the scene and how they can reach to that point. So from our point of view, the data analysis is as following. So it has a flow, which starts from making the decision of which data need to be collected, and then decide on how to collect the data and do the data cleaning part, and do the rest of the process. And of course, it's not like a linear, so that, I mean, it's not in a series, so that there is a feedback loop between these steps. So that, for example, when you do the data cleaning, so you may use visualization in that part as well, or for any other combination of the two parts. But the main flow starts with the decision and the data. And we believe if the company do the whole process, not ignoring these parts, it helps them to better and get the better understanding and insight of the data that they have. One more thing that I want to add here is the existence of the Center for Data Science at the Department of Informatics, which we are the energy wing of that, so that we are connected to a bigger community of people who are working on data, and they have expertise on data together with us who are working in this particular domain. I think we have a good expertise in data analysis. So once we have the data, probably one of the things that we are interested to do is the prediction. So prediction make a lot of sense in the domain of energy. So that, for example, you want to know about the weather condition, because that affect the power that you can produce with the turbines in the wind farm. Or you want to know about the height of the wave, so in the ocean, so that because that affects the the sailing speed and so on when you are working in the maritime transportation, for example. So what happens basically is that, I mean, this dotted line is the current time. So before that, of course, you know the information. There's no uncertainty involved. But after that, so there are some range of things that may happen, and a range of values that we may face in the future. So traditionally, we are interested into aggregate the data, so that instead of having the range, so we go for example, the average of the data, and then we provide with some statistical information like the standard deviation or similar. So what happens here? So that if we say that, for example, as an example, like for example, a storm gonna hit the western coast of Norway, so that it may hit Stavanger or Bergen. But when we do this aggregation, so that you may take the average location-wise here, so that you may say that on average the storm gonna hit Haugesund, which basically is not even an option. So that with this aggregation of the data, so you can say the same for the temperature and any other application of prediction. So aggregation and taking average is not the only way. It may help in many other applications, but sometimes we should go for other approaches when we are doing we are running the prediction. So ensemble models, and I mean coming up with distribution for each outcome is another approach, so that it make a lot of sense in many domains. So that, for example, these three actually values have the most possibility, and you see the distribution of each outcome. So that helps a lot, because then you know actually, even though this is in between, but there is no chance, for example, to have such outcome. So that helps a lot when you are doing the planning part. So now, once you have the data, you have predicted some stuff, then you probably want to make some decision, right? So that is another domain that we have a great expertise at the Energy Informatics Lab. I will go through one project that we are involved in, and I will explain what type of decisions, for example, we are dealing with. So here in this picture, you see some installations near Mungstad. So there are oil installations, and there are some fleets of vessels starting from this node on the right and shore, and it has to visit and do some task for visiting these installations. So what is happening? So the weather affects a lot, right? So that the objective here, the goal here is to minimize the cost, and cost comes from the fuel consumption, and fuel consumption comes from the speed and the power use, and that is affected by the weather condition. So what happens? So if the weather change, the wave height change, then it affects the sailing speed and the way we have to provide the power for. So, and that affects the cost. So it's important to have a good prediction. What is happening right now before we join this? So they had a base line, a base point. Let's say, for example, they pick the one node here, and then they look at their prediction for each day. For example, day 1, the weather is clear at this node, and then they assume that the weather is calm and clear for the whole area. The next day, for this particular node, the weather is in condition number 2, so they assume that for the weather for the whole area is in condition 2. But what we did here, by taking advantage of better forecast models and the optimization and the decision-making tools, we were now we are now able to handle a more precise version of the same problem. So in this picture, which is basically the same area in 9 different pictures, and each picture represent a different time. So the time difference between picture number 1 and 2 is like 7 hours, and that applies for the rest of the picture. And on the bottom, you see the different colors, the meaning of that. So then that is the height of the wave. So the darker the red, the higher the height of the waves, and that is a worse weather condition. So comparing to the previous model that I explained, so that here we don't assume that the whole area has the same weather condition at a particular time. So what's the effect of such thing? So that if we are able to handle the optimization part, the decision-making part, considering the accurate weather forecast location-wise, then we are able to escape from the worst weather and do a totally different sailing plan. So that, for example, so you see on the picture number 7, so that we have 4 different weather condition. So on the bottom of the area, and you see that the weather is much better. So that probably you can start with that part until the wave of the worst weather condition comes from the top. So I mean, yeah, you already noticed that. I mean, considering different type of information into account. So I mean, it adds to the flexibility, so that and that is equal to making money, or saving energy, or saving fuels. But at the same time, it adds to the complexity of the decision-making process. So that with the advanced optimization techniques, we are now able to handle such complex systems. So we did play with the data. We predict some stuff. We made some decision, but it's not usually easy to make decisions. So because there are many uncertainties involved. So when it comes to the decision making, so there are many ways to handle the uncertainties. So there are, like, for example, a stochastic optimization, robust optimization, scenario-based optimization. So there are different the decision making under uncertainties. Also, we can quantify the uncertainty, and that is when you say how likely is to expect a certain outcome, considering that the some aspects of the system is unknown. So that helps you to better dealing with the uncertainty, and with better dealing with the different aspects of the system. So uncertainty is very relevant. So in the domain of energy, in basically in any industry, you can simply face uncertainty. So the next point is system analysis that I want to talk a little bit of. So let's look at these 2 different system design for cabling of the turbines. So that you see 6 turbines. So that on top you see these 6 are connected with 2 cables, each connecting 3. And on the bottom, you see in the star layout where the turbines are connected to one artificial node, let's say, and that node is connected to the hub. So there are advantage and disadvantage of each design, right? And for example, if something happens, if there is a failure on a cable up there here, then you lose the whole power from these 3 turbines. So, but if, for example, if this cable in the bottom system is broken, then you only miss that one. But of course, the length of the cable is longer in the bottom system. So what I'm going to explain is that is the following. So for the sake of simplicity, I just removed the turbines because this is the way we at the informatics department see the problem. So on a graph. So let's play with the nodes and the edges that can be each node or edge can be replaced by anything basically. So depends on the problem or the industry that we are talking about. So it can be replaced by any subsystem. So assume that we have subsystem at each node. That could be, for example, turbines. So for each node, assume that there is a failure distribution. So over time, so that at a certain time, what is the probability of the failure, the failure probability of a certain subsystem, which I'm referring to a node, for example. And then assuming that we have this the distribution of failure for every node of a system. So then our job is to find the failure of the whole system. So to find the distribution of the failure of the whole system. And then you can compare basically the risk of these two different systems and come up with a better system design once you know what's gonna happen for the whole system. So that is, I mean, that was just one simple example. This is not limited to that, like the other application that I explained for the other parts. So you already noticed that, okay, so we have been involved in many different type of problems. So, I mean, and usually the problem that and the project that we are involved contains many aspects at the same time. It's not like one project only deals with data analysis, and the other one only works with the prediction. So it's usually the combination of different domains that we are involved in. So we have been working on many projects on wind farm design. So like location of the wind farms, the how to connect them, the cable routing, let's say. We have been involved in many transportation and in particular maritime transportation we have been working on recently, and there are some other and new type of projects that we are dealing with right now with hydropower and solar energy and so on. So among others, I want to draw your attention to a newly funded project, which is called Ocean Charger, and we are the leader of a work package called Smart Maritime Operations for Offshore Wind. So we know that there are many wind farms out there, and there are going to be much more in the future. So for each wind farm to be designed, so there are many things that need to be decided, including the fleet, so that there are different vessels that are needed for installations of the turbines and also for operating the turbines. So and these ships and vessels, they have to be in the future, near future, I would say, they have to be emission free, right? So that's why we are thinking of considering electric vessels to serve them. So when we are talking about electric vessels, then we have to think of the charging points, right? Because they have to get charged. So one of the decisions that, for example, we are dealing with in this project is to come up with the capacity and location of the charging points. Also, we have to decide on the type of vessels that we have to select from, and we have to design the scheduling and the routing of the vessels as well. So we joined this project a little bit late, so that if we were involved from the very beginning, so we could actually include many other aspects as well, like what I said. So from the beginning, and from the data side, and from the decision on the data, and also the prediction part, and other parts as well. So that's why I want to talk about a rough idea that we have, which make a lot of sense in many applications. I will explain one, but it's not limited to that. And this combines the different aspects, and that's what that actually shows the, you know, the ability of the energy informatics, because it's not only one field, so it's a collection of domains that we can cover in within the energy informatics. So let me explain about this idea. So assume that we have installations, so like oil or turbines, and then we have some devices like drones and vessels. Assume that the vessels are autonomous, same as drones, and they are both electric. And on the other side, we have assumed that we have a good prediction model. So we can. So this connects to the prediction and playing with the data. So you cannot come up with a good prediction if you don't know the how to deal and play with the data. So you need to have a good understanding of the data science. In order to be able to predict the data, you need to know the the advanced machine learning techniques. So you need, and then assume, let me explain the problem first, and then how we tackle it. So the prediction part is about to predict the weather and different aspects of the weather. So that, I mean, how the wave height, the wind speed, and many others. So how that affects the this idea. So we have drones, right? So that the drones cannot fly in any weather condition, so that they have to be in a situation that the speed of the wind is not so high, and so on. So what we are thinking is a sustainable solution for this whole system. When the weather is not so good, the the drones are not flying. They stay on this small autonomous electric vessel, and they get charged together with the vessel itself, so that they take advantage of this windy weather to get charged, so that they're gonna have some devices to be able to produce power from the wind and get charged. Once the weather is good, then they can go and serve the turbines. What they do, they go for monitoring the installations. So that saves a lot of money and time from the crew, so that instead of sending people to maintain the turbines, now we have the drones, so that they can go and monitor different stuff at the installations, and then they come back when they are done, and then they get charged. So prediction helps to plan, to better plan the whole system. And then we have to be able to program the drones, right? That also needs some expertise to how to get stable in different weather situations. So together, this idea provides a sustainable solution, because basically you are taking advantage of the the environment in a good way, right? So that when the weather is not good, so the drones and the vessels get charged. Once it's good, then they go and serve the installations, and basically there's no emission involved here. All right, so that is one example out of many that you can actually and simply see how different domains are connected within the, different domains within the informatics are connected to solve a problem within the domain of energy. So if we were focusing on only one domain, you couldn't actually achieve what you can achieve here by solving the whole system and having all the components at once. So with that, I want to conclude my talk and try to have the discussion afterwards, because there will be many more domains that we can touch upon. For example, high performance computing that I didn't touch, but it affects basically the whole other things that I explained, so that without having a good understanding of how to use the hardware, how to use them in an efficient way, you cannot come up with a good solution. And of course, at the end, so that you need a good software design to handle the problem that you are facing, and that software should not be very hardware specific, so that by changing and the development in the hardware, so that you cannot use the software. So this should be considered when you design the software. So I guess I would end here, and I want to invite my colleagues to join for the question and answer part.